Welcome. The topic for today is geodesics on a sphere. One of the basic notions in Euclidean geometry is that of a straight line, or a straight line segment connecting 2 points. So it is important, if you want to study geometry on other surfaces, like the surface of a sphere, for example, to find a substitute for that. There are no straight lines on a sphere, and instead, one notion that is a good substitute for a straight line is that of a geodesic. Geodesic between 2 points is the shortest possible curve. Then if you think about a plane and you take 2 points on the plane, the shortest possible curve between 2 points on the plane is a straight line segment. So you define the distance between 2 points on the plane to be the length of that line segment, and this agrees with the notion of a distance in Euclidean geometry. So we want to find out today what the geodesics on a sphere actually are. So first of all, we make a little simplifying assumption. That is, we're going to be studying a sphere whose radius is 1. This is not really does not bring us any loss of generality, because in particular you can change if you have a bigger sphere, like for example the surface of the Earth. You could think about it as a sphere of radius 1. You just have to change the units. For example, if your units are thousands of miles, so 1 unit is 1,000 miles, then you actually get a pretty big sphere when you think about a sphere of unit length, of unit radius. So, and this simplifies a lot of the calculations, because then this allows us to get rid of that pesky radius r that appears in a lot of formulas, but is actually quite irrelevant to the main things we want to learn about the spheres in this course. So our spheres will always have radius 1. So first, let us define again what a geodesic is. So to do this, because geodesics are curves, I first remind you of a definition of a curve. So for us, a curve in R3, so our sphere will sit inside the three-dimensional space. So a curve in R3 is a smooth function from an interval a to b, closed interval, into R3. Or if you wanted to have an infinite length curve, then you can replace this closed interval by the real line. So it's a C, the curve we denote it by C, and then it has 3 coordinates, x, y, and z. All of them depend on this variable t. And smoothness means that this x of t, y of t, and z of t possess all derivatives of all possible orders. Secondly then, we say that, so that's a curve in R3. What's a curve on a sphere? Well, that's just a curve whose image actually lies on the sphere. So it's not a curve that sort of sticks out of the sphere or something. If you actually draw the curve, it's completely contained in a sphere. And remember, for us, sphere is hollow, so it's only a 2-dimensional object. So the notation for a sphere is of radius 1, centered at the origin, would be S2. The 2 really represents the fact that it's a 2-dimensional object. S1, for example, would be a circle. And finally, a geodesic on that sphere between 2 points. So I pick 2 points on the sphere, and I would like to know what is a geodesic between these 2 points. That is the shortest possible curve. So shortest possible smooth curve, right? All our curves are smooth. Okay, so we're going to prove that if you take any two points on a sphere, then the geodesic connecting them is an arc that is part of a great circle. So what is a great circle in a sphere? That is a circle it's essentially a circle in R3 that lies completely on the sphere, whose center is the origin. In other words, if I can cut the sphere in half by various planes, and exactly in half, And whenever I cut it exactly in half by any plane, then the intersection of that plane with that sphere would be a great circle. So it's sort of the circle of the greatest possible radius on the sphere. So we claim that geodesics actually are, the geodesics on the sphere are actually parts of arcs of great circles. So let's state this as a theorem. I have a picture here for you that I prepared, but so let's put in a theorem here. So theorem. A geodesic on S2 between any 2 points is the shorter arc of the great circle through P and Q. Okay, so suppose I take 2 points on a sphere, P and Q. Then, in order to simplify my calculations, I'm going to position the sphere in such a way that it fits nicely into the Cartesian coordinate system. So I drew here in blue the Cartesian coordinate system x, y, z, and I'm going to place my sphere with the 2 points PQ so that the center of the sphere is equal to the origin of this coordinate system. The radius of the sphere is 1, right? So all these points here that intersect the axis x, y, and z intersect them 1 unit away from the origin. And furthermore, I'm going to take my point P to be the north pole of this sphere. Yeah, if I have a sphere and the point sort of started life somewhere, I can always draw the Cartesian coordinate system so that the z-axis actually goes through that point. So my point P would be the north pole of that sphere, so its coordinates will be Cartesian coordinates. So note the axes, the blue axes, are Cartesian axes. So the blue coordinates correspond to Cartesian coordinates. Yes, here you have a little legend for this. So the coordinates of that point P are 0, 0, 1. So the point lies on the x-axis. Sorry, the x coordinate is 0, the y coordinate is 0, and then the z coordinate is 1. Second simplification is this. So point Q then is somewhere else on the sphere. So keeping the center where it is and the north pole where it is, I'm going to rotate the sphere so that the point Q actually lies in the xz plane. Okay, so its y coordinate is 0. If you don't want to rotate the sphere, you can as well just rotate the axis of the Cartesian coordinate system to place it like this. So the coordinates of Q are some value of x, I don't know what it is, x0, the y value is 0, and the z value is z0. And now what does the theorem actually say? So if I think what is the great circle that goes through P and Q, that is the great circle that is entirely contained in the xz plane. Okay, I'm just going to draw a little picture here of just the xz plane. So I'm just going to stick it in here. xz. Okay, and now the intersection of the sphere with this plane is a circle of radius 1. And here, on top of that circle, I have the point P. Okay, and somewhere here, I don't know, somewhere here I have the point Q. So the theorem now tells me that the geodesic on S2 between points between points P and Q is the shorter arc of the great circle that goes through P and Q. So here I have the great circle that goes through P and Q. It's a circle of radius 1. It's exactly what you get when you intersect the sphere with the plane xz, so with the plane whose equation is y equals to 0. And there are two arcs on that great circle that connect P and Q. There is this arc here, which I'm going to draw in a little thicker color. And then there is the other arc, namely this one. So there are two arcs that join P and Q in that great circle. One of them is shorter than the other, and that's the geodesic. Okay? So the shortest distance, the shortest possible curve between P and Q is going to be this one, of course not that one. Now you immediately notice that in some cases there are actually two choices. When P is the North Pole and Q is the South Pole, or if they are exactly antipodal points, then actually both of these arcs give you a geodesic. So in that case, in fact, when the points are exactly on the antipodal points on the sphere, there are in fact not only two geodesics joining them, but infinitely many. Okay? And we're going to draw a picture at the end of this video to visualize that. But at the moment, I'm claiming that this is the geodesic. So let's compute the length of it. This is just a circle, right? And the circle is has radius 1, and here there's an angle which I denoted also on the big picture by phi 0. How do you define an angle? This is an angle in radians, right? So an angle in radians phi 0, so in radians always, is equal to the circumference divided by the radius. Yeah, I mean that's how angles in radians are defined. In particular, if it's an 180-degree angle, that's like half the circumference of the circle, so that's pi divided by 1, so pi. In particular, in this case, the radius is 1, right? This is 1. So this is really circumference. So that means phi 0 is equal to the circumference of that circle. But in fact, I'm asking the opposite question. What is the circumference of that? So what is the length of that curve? That's equal to phi 0, right? So the length of the shorter part of the great circle through P and Q is phi 0. Okay, sorry for squeezing it down here. It just says the length of the shorter part of the great circle through P and Q is equal to the angle phi 0. Okay, we think usually about angles as just measuring the angles, but in particular on a circle, the angle on a circle of radius 1, the angle is the same as the length of the circumference. So that means the length of that curve is equal to phi 0. Okay, so let's now go back to our picture. I mean, we're not done yet. We just explained what the theorem means. What else is it that we need to do? Namely, we need to show that if we take any other smooth curve that lies on the sphere that connects the points P and Q, that its length will be greater than or equal to phi 0. Phi 0 is the length of the arc of the great circle, and we claim that's the shortest possible. So that means if we take any other curve that connects P and Q, we should get something that is longer. Okay, so we start by saying, so let C, and in fact I'm just going to go from 0 to it doesn't matter, let's say capital T into S2, which is contained in R3, be a curve such that C of 0 is P and C of T is Q. So that means the curve begins at P and ends at Q. So it's a curve connecting P and Q. We want to show, so I mean on the picture it's just some curve. It's really the image of C here. And I'm trying to show, right, that the length of this curve is actually larger than the length of this arc of the great circle. So we want to show that the length of C is greater than or equal than phi 0. Which is, right, the phi 0 is the length of the arc of the great circle. So that will show you that the arc of the great circle is the shortest possible curve. Okay, so I have my curve C, and C of t is given by x of t y of t and z of t. So what's the length of C? I'm going to denote actually the length of C, the length L. Okay, I'm just going to write it like this. L of C. This is the length of C is equal to the integral from 0 to t of the square root of dx over dt, or I guess I can just write it the same way we did in the last video, so it's just x prime of t squared plus y prime of t squared plus z prime of t squared dt. That, if you recall, was just a formula for length of a curve inside R3. The curve at C, of course, lies on the sphere, but it's also part of R3, so that same formula still applies. And I'm going to use I'm going to use spherical coordinates here for this. And in this picture here, I also wrote down this should be spherical coordinates, not polar. Spherical coordinates. Of the points P and Q. So what are the spherical coordinates and why are they only 2 rather than 3? Okay, so one of the spherical coordinates is always the radius. And the radius in this case is always 1 when we're on the sphere. So I only need 2 of the spherical coordinates to describe points on the sphere. The 2 coordinates are, the second one is just the angle that a point forms with the z-axis. So that's the phi coordinate. You see it on the second coordinate everywhere. So of course P lies on the z-axis. So the angle that the z-axis forms with itself is 0. So that means this here, phi, is 0. While for Q, the phi coordinate is equal to phi 0. The other coordinate is the theta coordinate, which is what I get when I project that ray down onto the xy axis. And that's the angle that that projection forms with the x-axis. However, both of these points, P and Q, lie on the plane xz. So when I project them down onto the xy plane, they both land on the x-axis. So the rays from 0, 0, 0 to the points form angle 0 with the x-axis. So that's why the first coordinate, the theta coordinate, is always 0 in their case. However, right, if I take any point here on the curve, I can project it down. It doesn't necessarily need to land on the x-axis. So it can form some angle theta. And I'm not going to draw it here, or maybe I will. And it forms some angle phi with the z-axis, right? Because there's no reason why this curve could not stray away from the great circle. Okay. In part 2, we'll finish this calculation.